So when your tasks do not depend on each other, they should not wait for each other as well, right? So that is the core philosophy behind this parallel design pattern. So when you have multiple tasks and they don't depend on each other, so why not run them parallelly? So instead of, so we have a one agent, they will, you can leverage multiple agent, they will work parallelly so that you can do more simultaneously. So if that kind of use case you have, where you have the flexibility to run agents parallelly, then you can go with this parallel design pattern, system. So that's what we will be talking about in this video, like the parallel design pattern, which is also called as octopus design pattern or fan out and gather design pattern. We'll see the underlying architecture and why it is effective and when we should use and the limitation and trade-offs, and we'll see some use cases in life science domain, how we can leverage this. And again, we'll have a hands-on wherein I will demonstrate how to quickly build an parallel design pattern of an agentic AI system, where we will leverage multiple agents that will run concurrently and will gather the output. We'll see in hands-on. So without further delay, let's jump to the topic. So this design pattern is very simple, like called parallel or fan out and then gather the design pattern. So basically when a user request, so it comes to an agent who will delegate its task to, let's say, some 3 sub agents which will run parallelly, and then will get the output from all the agent, and then there will be gathering and we can summarize the output and give it. So that's the pattern. So what is this pattern is all about? So basically the core idea is like do more at the same time. So that means multiple specialized agents execute your task independently and concurrently, and then their outputs are later combined. So that's what, instead of waiting for steps to finish one by one, for example in sequential 1, 2, 3, 4 they go in sequence, so second has to wait till there is a dependency is there. So here instead of waiting for steps to finish one by one, the agent fans out work in parallel. So that's what same logic I have talked about, also called as octopus pattern or parallel pattern or fan out and gather pattern. So the main benefit is time, right? That's why called reduced overall latency. That means you will get the output very quickly, and so it's faster information gathering, and independent agents don't block each other, and again it enables diverse perspectives. So what it mean by, like for example, let's say you want to do some task. So what you can say that same task you can give to 3 agents separately to just check what each agent will come. So that way you can have a diverse perspective from 3 different agents as well. Or you can have task 1 by this agent, task 2 by this one, task 3 by 3 independent tasks you assign to each agent and collect it. Or you can have, as I said, different same task give to 3 different agents, and then look for their different perspective. So in such use cases, this pattern is very effective. But main thing is these subtasks should not depend on each other, and otherwise running them sequentially will waste your time. Okay. So when should we use? Same thing, independent, concurrency and speed coverage matters more than step-by-step reasoning. So typical examples like gathering data from multiple external sources independently. You can download these multiple sources parallelly as well. And another example, interestingly, evaluating multiple hypotheses at once. Then comparing alternative solution in parallel. What I say, like same task give to 3 problem and see alternate solution A, B, C, which one is good. That kind of use case we can go for this parallel pattern. But the main limitation is what? Higher immediate resource, because 3 agents are running parallel, so your resource demand will be very high. You might see a spike in the all usage, agentic usage you will see, and again increased token consumption, and you may need more complex aggregation logic if the tasks are independent, and each task, let's say, generate different types of output. Then you have to ultimately gather them, right? So this gathering step might be more complex. It's not, see, it's a trade-off, right? Let's say you are parallelizing 10 tasks and 10 agents are running, and finally everyone is joining at the one step, which is aggregating all output. So this could be a bottleneck, right? So that's why it's not like always, oh, I have more resource, I will go for all parallel, right? So you have to see how the aggregation logic also, if whether it is complex or simple. And also it can happen that conflict output you might get from tool 1, tool 2, sorry, agent 1, agent 2, you may get conflicting output. So that's what faster execution comes at the complexity, at the cost of complexity, at the aggregation level. That's the main limitation. Otherwise it's good to go when we have more parallel. There is no harm in it. Okay, so with that we will do a very nice hands-on where we will see practically how to build this system. Okay, so let's go the parallel design pattern again. Once again repeating, like we will be using OpenAI SDK agent to do that, and so for that we will be importing. And you have not know how to do that, you can go and watch my previous videos where we talk in detail how to build these kind of intelligent systems. Okay, so very simple. You just import all the libraries. Main are the agent and runner to define and running the agent, and also we need function tools for tools, but here I think we are not using it. And these two we need for building a local LLM to use it. So I will be using my local GPT OSS model, which is a reasoning model. I will be using that. Okay, so let's run this library, and here I am defined. Let me comment this. I will be using GPT OSS model. So defining a client which is running in my local system, and using the client I'm defining the model GPT OSS. Okay, so let's run it. So here I'm 3 agents I'm creating. Okay, so for now it's very simple dummy examples. You can say the GC content calculator. So like given a DNA sequence, calculate the GC content percentage, and here I'm explicitly telling that restrict your output to 50 words or less, otherwise it will generate more output and will consume more token. So we have one agent GC content, we have second agent coding agent. So this will be able to, given a DNA sequence, it will calculate possible coding region, that means start and stop code and those kind of thing. And the third one is restriction site finder. So again we'll give the same DNA sequence, it will call all the E. coli restriction site, that is GAA, TTC in their position. So we have now 3 agents defined. So now let's see how do we call them. So I am creating a workflow here. So this is the Python function parallel pipeline. It is asynchronous and it will take a DNA sequence, and here we are calling 3 agent, right? Runner.run GC agent, coding agent and restriction agent. I'm passing all the 3 DNA sequence here, but here I'm gathering the output. So from async IO package we need to gather the output of all 3 asynchronous functions. Okay, so now we have 3 processes are running and we will be gathering the output. And here in this example I'm simply printing it, returning it, but here we can have one more agent defined which will take all this output of all these 3, and then maybe it will do summarize and it will do something else. Finally it may be generate some markdown format. Those can be done, but for now I will just print this report. Okay, so this is why workflow is defined, and now let's run it. So I will pass this DNA sequence and call this function and let it run. Okay, so what it will do now, it will now think, because I'm using the reasoning model, right? So it will think and it will parallelly execute all these 3, this one, and it will call the output. So let's go to the traces. Okay, let me refresh this page. Okay, it came. Okay, so I click there. Okay, so far it's not yet generated the response. So let me pause my video and I will get back once this results is done. Okay. Okay, so it completed now. This is the output we got. GC content, the DNA has 12 something something, and it's 40%. For coding region, it answered like this, and restriction site it answered like this. Okay, so let's see the traces here. This is the what happened. Okay, so first it called the GCC agent, and then we got the output over here, and it called this agent here, second one coding region, and got the 3. You can see that at the same, it spans from here. The starting point is same. That means these 3 were called same time, even though the time of response is different, but these 3 are called separately. So that's how you design a system like define multiple agents and you parallelly run them and gather the output from each of the agent. And then here we did not do anything, but you can further refine it and further pass to and one more agent, and then you can do. Also, we can combine these hybrid design patterns as well, sequential to planning, based on the output what you got. Maybe you can further define some task and execute it like that. Say you can mix and match, but you get an idea like how the parallel design pattern works. Okay, so yeah, so in the next video we will talk about the multi-agent design pattern, which is so where each agent is very special. So it's very similar to like this parallel kind of thing, but here we have three agents and each agent is very special. That means we can have each agent equipped with some other tools. This agent maybe some other tools expertise, this agent expertise. So basically it's just not three steps we are calling here. We are calling three agents example. I mean each agent is more special. So that's what we will be talking about in the next video. I hope you like this and I will see you in the next video. Thank you. Bye.